Assalamu alaikum, dear students. We're back with another video lesson, and hopefully this session will be the last session or the last video lesson in chapter 6. To be honest, I was planning to finish this in the previous lesson, but things sometimes doesn't go as planned. So forgive me if it is, if it was not covered in the previous video lesson. So after talking about the efficiency or transfer efficiency, now we ended up at section or chapter, you can say section review clearly. That is for chapter 6, section 3. All right, so this is clearly, it says the root mean square current that a single coil of an electric guitar produces is 0.025 milliamperes. The coil's resistance is 4.3 kilo ohms. What is the maximum instantaneous current? What is the root main square electromotive force produced by the coil, and what is the maximum, let's say, what is its maximum value as well? So clearly we've been through questions like this a lot. So we have, what do we have? We have a current, you can say, or you could just say the I effective, yeah? I effective. What is I effective? That is 0.025 milliamperes. Don't forget, millis 10 to the power -3. That is amperes, you can say. The coil's resistance, so R is 4.3 kilo ohms. What is the maximum instantaneous current? And of course, what is the root main square value and all that? Okay, so how about we take a look here. These are pretty simple. I believe we've solved questions like this a lot, so I'm not going to spend time over this, but I'll just give you the idea. So we have the instantaneous value, which is basically, or my bad, okay? The root main square, all right? It says the root main square current, or you can say also effective one, which is basically 0.025, that is milliampere. That is basically what we have, as you can see here. Okay, and then we have the resistance and all that. What is the first question? It says, what is the maximum instantaneous current, you can say. The maximum instantaneous current here, we said I effective basically equals to the maximum current divided by the square root of 2. So I maximum, using the cross multiplication, equal to I effective times the square root of 2. We have I effective times the square root of 2. You just multiply the 2, you get 3.5 times 10 to the power -5 amperes. That is the first part. Second says, what is the root main square electromotive force produced by the coil? What is the effective voltage here? So how do you find the effective voltage? Remember, we have I effective, we have the resistance. Can I find V effective? Absolutely, yes. So we'll say V effective equal to, remember this, if it is effective, we'll have to use the effective value. If it is maximum, we'll have to use the maximum value with, okay? So we cannot use effective and maximum here. You have to be careful in here. So V effective equal to I effective times the resistance here, which is basically this much. That is the effective, the one that we had over there, and of course multiply by the resistance, which is 0.108 by rounding. That is the voltage. And then what is the maximum value? The maximum value for the voltage, we do know that it is V effective times the square root of 2. You just plug in the numbers, you'll find the answer. Okay, now take a look at this question. It says, why do we charge a capacitor under DC voltage? We've mentioned this before. We said capacitors can only be charged with DC voltage. And why is that? Because if it is AC, it is, for half a cycle, it is a positive, let's say one plate, we have two plates. Sorry, if it is AC alternating current, for half a cycle, one plate, or this plate, let's say, will be positive, the other plate will be negative. For the other half of a cycle, this is going to be negative, and the other one is going to be positive. If I just remove, let's say, focus on one, let's say, plate of capacitor. For half a cycle is positive, the other half is negative. So this half and half, of course, they cancel out. They cancel one another out. You can say we'll end up with no net charges on the plate. So that is why we cannot use AC. The capacitors has only, or has to be charged only with direct current. And that is the answer. To avoid the continuous charging and discharging caused by the alternating current here. Okay, now we have another question. Says, what is the average value of the current over one cycle? AC signal. So the average value, remember this, for half a cycle is positive, the other half is negative. So what is the average value? You add them, of course, and you divide by 2. So, but in this case, of course, you can just say positive and negative. If it is, let's say, 5 positive, 5 negative, you get a total of 0. Okay, so we can say the average, is it the current? Yes, so we'll say the average, the current over one complete cycle is 0. But there is another part of this question which is very important to know. It says, why then is a resistor heated by an AC current. If we say the average current over one cycle is 0, then how come that a heater, right, can heat up, let's say? Don't we say there is 0 average, or let's say the average current is 0? We'll say yes, but remember, heaters normally, we can say waste electrical, or you can say waste energy. Or in a different way, you'll say they'll convert electrical energy to heat energy, which is, you can say convert electrical energy to heat. You can consider that as a waste, but of course this waste is useful because you're heating, the purpose is heating, let's say the room or whatever this thing. Okay, the answer to that, of course, whether current is positive or negative, we'll use the equation for power that is basically I squared times the radius. That is the power loss equation, correct? So when we say I squared, or the current squared, whether if it is positive or negative, it still turns out or comes out positive. Okay, let's say -5. -5 squared, you get what? You get positive 25, correct? So as a result, you can say always get a positive value. So we'll say the heating element will heat up regardless to whether the current is positive or negative, because it is I squared times the radius. Okay, and of course that is the question, times the resistance. I keep saying radius. Okay, I don't know why. However, a resistor is heated by an AC current because the heating effect depends on the square of the current, which is I squared, which is always positive. The result in power dissipation and heat generation regardless of the current direction here. Okay, take a look at these two questions. What do they say? The average value of the alternating current in one cycle, it is equal to what? We said it is equal to 0. We can charge a capacitor under what? Under AC voltage, under DC voltage, source only, under an AC voltage only, could not be charged anyway. We'll say we can charge a capacitor under DC, direct current only, okay? So, by the way, if they were written, for example, a battery, a battery would also be a DC, that would also work in there. Okay, so under a DC voltage source only here. Under, okay. Perhaps there is something missing here. Perhaps this one they mean under AC and DC voltage source only. Or could be battery and AC voltage only, but that will be incorrect because of the AC. Under a DC voltage source, that is correct. You can see here, there's also something missing here. I don't know why, but just in case, it could be battery and AC again, or it could be something else. Anyway, but it has to be either let's say a source that provides only DC or just DC only. Otherwise, it cannot be charged. Okay, now, summary of chapter 6. I really want you to go through this because that would summarize the entire thing of chapter 6 here. Okay, now let's go to another part of the questions which are also very, very important, and that is standardized test preparation. Take a look. These are truly important here. The first one says, which of the following equations correctly describes Faraday's law of induction? And of course, we had quite a number of equations, yeah? But which one of these would represent Faraday's law of induction here, and which one is the correct one? Well, take a look. The first one here says what? Negative n AB. So far, so good. But here says tan. Oh, can I use tan theta? The answer is no. So you can put this aside. This one has no negative. Put it aside. What about this one here? It says negative n. That is delta AB cosine theta, right? Divided by delta t. That is really good. Let's keep it aside. What about this one here? It says basically electromotive force induced, that is mutual induction AB cosine theta over delta t. That is supposed to be negative n, not m, so this is incorrect. So we're left with option C. So we can say option C, it is the correct answer here. Okay, now take a look at question 2, which is also very interesting. What does it say? It says, for the coil shown in the figure below, what must be done to induce a clockwise current here? So now take a look. It says clockwise current, yeah? So we have, okay, so we have this. If I take one turn here, of course, it's going to be something like this here. So as you can see here, even if I don't do this, let's just make this one a bit nicer maybe. Okay, so in order to make it clockwise, let's say this is 12, 3, 6, and 9, yeah? So in order for this to be clockwise, what does it mean? That means the current has to go this way. Let's use a different color so you can see the difference here. that has to be clockwise. So if it is clockwise, it has to be this way, and then this one, and then this one here. So this here, of course, we'll say this way. That is basically clockwise. If not, just for example, you can somehow see or imagine the coil is being tilted this way so that you can see it at an angle. Once you see it at an angle, for example, here, so if that is the case, so we'll see that if it is moving this way, that is obviously clockwise here. So, but we've learned, okay, using chapter 5, let's say, we've learned that if that is the case, use the right-hand rule. All right, align your fingers, let's say, in a way, the same way you can say that the current is flowing. So if the current is flowing this way, that means this side is going to be what? This side is going to be north, the other side is going to be south in here. Okay, now here comes the interesting part, okay? So let's get this one over here and see the importance of this one right here. So take a look. Now, what are the options that we have, let's say? So what does it say? It says either move. So how can we do that, by the way, yes? Okay, what must be done, all right, to induce a clockwise current? So here's the direction of the clockwise current, but if I do this, you can see this is the direction of the current all the way down, by the way, okay, there. So if I do this, this side is going to be north, the other side is south. Okay, in another word here, take a look at the options. Move the north pole of a magnet. Oh, so it's talking about magnets here. So how can I make this side of this coil to behave as a magnet, or so that this end of the coil becomes south? Okay, because if this end is south, that means the current is, let's say, moving clockwise, the other end is north here. Okay, so there are two options. We've learned some options here, yeah? Remember this, if I bring a south pole here, so south pole, and this two, of course, this is also south, so what do? They repel one another using Lenz's law, don't forget, yeah? So if you bring a south pole, we've learned this side will also be south because these two will repel one another, yeah? There was another way, actually. So if I have a magnet, let's say, and here is the magnet here, and if this side is north and this side is south, but if I move away the north pole, now once again, these two are going to oppose one another. If this is north, if this is north, this is going to be south, so that they can attract one another, so that it doesn't allow this one to move further away. So there are two options or two ways they can do. First of all, this has to be north. In order to get this end of a coil to be south, I'll either have to move a magnet, or you can say south end of a magnet closer into the coil, or I'll move the north pole of this magnet away. So here's what we need to do, let's say. So let me emphasize on this. We'll use this one, and of course we'll use this color as well, just to indicate. So you're either going to move the north pole of this magnet away, or you're going to insert the south pole of this magnet into the coil, or closer to the coil, so that you get south, south, and of course north once that is moving away. So let's take a look at the options and see which one is the correct option. Either move the north pole of a magnet down into the coil and move the south pole of the magnet up and out of the coil. Is that true? It says move the north pole down. That is incorrect. So because if you move the north pole down, this side is going to be north as well, so you will not get south. And if you don't get south, that means the current will move the other way, counterclockwise, you can say. Okay, what about this one here? It says either move the south pole of a magnet down. Move the south pole of a magnet down. All right, this part is so good so far. And then says into the coil, or move the north pole of the magnet up and out of the coil. So if not, let's say, move this north pole out, let's say, and of course up and out of the coil here. So that is also true. So we can say this is correct. But let's take a look at the other option as well. It says move either poles of the magnet down into the coil. That would be incorrect. And then move either poles, or let's say either poles of the magnet up and out of the coil. That is also incorrect. So the correct option will be option B here. Okay, and of course you can see the direction of the current as well. I forgot to mention that. It says, which of the following would not increase the electromotive force produced by a generator? Okay, rotating the generator coil faster, or increasing the strength of the generator magnet, increasing the number of the turns of the wire in the coil, or reducing the cross-sectional area of the coil. Okay, so which of the following would not increase the electromotive force induced by a generator? Of course, is going to be reducing the cross-sectional area of the coil. Once you do this, that will not increase the electromotive force generator there. So of course we've mentioned that for, let's say, increasing this, how about we, for a generator, yeah? We can say, of course, electromotive force here, it's basically negative NA, let's say B cosine theta divided by delta T, yeah? So the first one, not this one, not this one. Okay, so let's just move this aside. Let's forget this here. So just remember that reducing the cross-sectional area, of course, it is going to, let's say, or it will not increase the electromotive force produced by a generator. Then that will be it. Yeah? Of course, we can use the same equation that the one that I have done, by the way. If you reduce that one, of course, the electromotive force that is going to be induced will be less based on the equation that I use as well. Now take a look at this one. This also could be a little bit misleading here. So see why. By what factor do you multiply the maximum electromotive force calculating, or to calculate the electromotive force, or the root mean square electromotive force for an alternating current? Okay, so we do have the alternating current, yeah? But by what factor, let's say, do you multiply the maximum with here? So we'll say normally I effective or root mean square equals to what? Equals to V maximum over the square root of 2. So if I move this V maximum here, instead of writing it here, so let me just write it here. So in this case, of course, we can say, let's erase this one here. So instead of this one here, I'll just write 1 here. So do not just say the square root of 2 because that'll be incorrect here. So now we'll multiply the whole thing, 1 over the square root of 2 with the V maximum. Then, of course, you get V root mean square, and that is going to be option C. Okay, take a look at this one. It says, a coil is moved out of a magnetic field in order to induce an electromotive force. The wire of the coil is then rewound so that the area of the coil is increased by 1.5 times. Extra wire is used in the coil so that the number of turns is doubled. So let's take these into or precautions, let's say, or take a look at this. It says reduce the wire. Okay, here the coil is then rewound so that the area of the coil is increased to 1.5 times. This is the area. Extra wires so that the number of turns double. Okay, the time in the coil moved from the field and all that. The time says reduced by half. The magnetic field strength remains unchanged. How many times greater the new induced electromotive force than the original electromotive force here? By the way, here's the equation that we need to use. Yeah, so I'll say electromotive force induced negative N. We can say AB cosine theta divided by delta T, by the way. So here's the equation that we use, by the way. If something is changed, you can do that. If not, whenever it says by factors or by what factors, you can just write the equation, by the way. Yeah. So instead of writing the equal sign, you could just say electromotive force that is induced, that is directly proportional. It is directly proportional to N, of course. You can say that is directly proportional to A to B. You can say cosine theta, and of course inversely with a delta T here. So watch this. It says the number of turns is double. So if I double this one, that is 2. And then the area, as you can see here, it says the area was what? Where's the area? The area increased by 1.5. Yeah. So here's 1.5. The magnetic field strength stays the same. If it stays the same, that means I can just, let's say, remove it from the equation. What about the time? What happens to the time? The time is reduced by half. So if the time is reduced by half, we can write half in here. Okay, so what would be the case here now? Or the result in here now? So 2 times 1.5, sorry, that is 3. And then this is over 1 over 2. This 2 goes up, so it becomes 3 times 2. 3 times 2, of course, it becomes 6. So you can say this, or the electromotive force that is induced, of course, it is going to be increased by 6 times here. And that is the correct answer. Okay, take a look at this one. This is also very interesting. It says, use the passage below to answer these questions, 6 to 7. A pair of transformers connected in series, as shown in the figure below. Very, very, very interesting, guys. Take a look here. It says from the left to the right. Before we're going through the choices, take a look at this. You can see there's 1,000 turns, there's 240,000 volts, there's 50 turn, and then on this one here, there's 600 turns, and then there's 20. If we take a look at only the transformer that is to the left, this is to the right, yeah? Okay, so we can say left transformer, this is right transformer. Okay, so if we look at this one here, more turns, you can tell from the diagram, more turns, less turns. So going from left to right, it is a step up or step down. You have to tell me step down transformer. What about this one here? This is also step down transformer because there's more turns in here compared to this, even without looking at the numbers surrounding these two transformers. So let's go through the questions. So it's from the right to the left. What are the types of the two transformers? So like I said, moving from right to left, or left to the right, my bad. So moving this way, that is, let's say more turns, less turns, more turns, less turns. So these are both step down transformers. So both step down, step up, step down, whatever. One step down, the other one step up. One step up, the other one is step down. This is incorrect. So the correct answer, both are step down transformers. That is the answer to this. Now look at the second part of this. It says what? What is the output potential difference from the secondary coil of the transformer on the right here? So which transformer is to the right? This is the right one. This is the left one. It says, what is the voltage here? This voltage. So how do you find this voltage here? There was something I want you to be very. This is pretty much easy, actually. There's only one idea in this. And of course, we're going through the idea right here. Okay, so what is the idea in this? We will say, oh, not this. Okay, let's get this back. Okay, so what is the idea on this? The only idea is we're going to use or have, okay, let's uncover this. Okay, so we're going to find, using these information to find the voltage here. But this voltage here, you can call it V final here, okay? Or not V final, okay, V2. Okay, so this is, you can call it V1, and this is V2 clearly. But you can see that these wires are connected. These two transformers, you can say connected. So whatever is the V2 here in the secondary transformer coil here, that is going to be the same as the voltage here. So we can say V2 here, it is equal to V1 on the other transformer here. Using V1 and all the other information, the number of turns, we can find V2 here. So let's do this one here. So for the first transformer, we can say V2 over V1, which is equal to N2 over N1. That is basically for, remember, for the transformer to the left. Left transformer. Okay, so V2, V1, N2, N1. What is V2? V2, it is unknown. That is, we're talking about this one here. So here's V2. V1 is 240,000 volts. It is equal to N2, clearly 50 turns. And then N1 is 1,000 turns. Okay, so you do the math, of course, you will find V2 here. So that is basically these two cancel out. Then these two cancel out. That is clearly, you do the math, of course, you can tell me what is the answer here. That is going to be V2. We're going to take a look at the answer and see what is V2. That is going to be in volt. But don't forget, this V2 here, like we said earlier, is going to be the same voltage that is here. So we will say, now for the transformer that is on the right here. So we'll say right transformer. For right transformer, we'll use the same equation, yes? We'll say V2 over V1, that is equal to N2 over N1. But look, V2 here, it is basically the secondary voltage here. That is what the question wants. So we'll say V2, okay? And then divided by V1. So remember, these two are equal. So V2 for this equals to V1 for this. So we're going to take a look what was the answer. And then N2, where's N2 here? That is N2, which is 20 turns here. What about N1? N1 is basically 600 turns here. Okay, so let's find, or let's see what is this, and then of course we'll get back to this. So V2 where 12,000 volts. 12,000 volt. Let me erase this one so that this point doesn't cause confusion. We'll say 12,000 volt, yeah? So you cross multiply, of course, you'll find the answer there. Okay, so let's do this right. That is 12,000 multiplied by 20 divided by 600, yeah? So 1212, that is basically 2 times you can say that is 2, this is 1, yeah? So that is basically about 400, yeah? 2 times 2, that is 400. So it's going to be 400 volt, yeah? So do we have 400 volt there as a multiple choice? There should be, yeah? Where's 400? Ah, here. So it is clearly 400 volts. Okay, so as you can tell, there's no idea in this. The only idea is once you find V2 here, this V2 is the same thing as V1 for this transformer. Then using V1, N1, N2, you'll find V2 for the right transformer. And that's all of it, yeah? Okay, now take a look at question 8. Also, question 8 could be a little bit confusing. Or perhaps this is the sort of question that it might send you to the other side. I don't say, okay, anyway, hope you understood what I meant. So it says what? The maximum value for the current and potential difference in an AC circuit are 3.5 amperes and 340 volts, respectively. How much power is it dissipated in the circuit? You really have to be careful here because it gives you something, right, that you are not going to use directly here. So you might, whenever you see, for example, voltage and potential difference, you might just go ahead with, or using this, let's say. We do know that, let's say, power equals to current times the voltage here. But what sort of current and voltage here? Remember, we said for the power dissipated, or for the power, let's say in general, we will use effective values here, okay? So not the power effective, we'll just say power equals to this much here. Or normally we just say power, or whenever it comes to power, you have to use the effective values here. But here's the thing. Are those values given effective? No, these are maximum here. So don't forget, maximum current and maximum voltage here. So how do you convert maximum to effective? We'll say I effective, it is equal to I maximum here divided by the square root of 2. Once you find this, then of course you plug it into this one. What about for the voltage? You do the same thing, yeah? So we'll say V effective equals to V max over the square root of 2. So you have maximum, which is 3.5 divided by the square root of 2. You'll get the I effective, plug it into the equation, and then for the V effective, you have V maximum, which is 340 volt, divided by the square root of 2. You get V effective, then of course you can use the equation of power safely. Otherwise, it would be incorrect. Okay, that is for this one, which is also very interesting. You might just, like during the time, of course, you're confused. Perhaps you might wear it and stress a bit. So whenever you see current and voltage, you might just multiply them, and of course, you will get a wrong answer. Because for power, it has to be the effective values here. Now take a look at this question. There's also another question that is very easy. Just the application of the equation. You have maximum value of current. That is obviously 12 amperes. What is the root mean square value for this? So in order for the root mean square value, or I effective here, of course that is I maximum divided by the square root of 2. That is just the application of the equation, nothing more. Now what about question 10 here? It says, what is the purpose of a commutator? Let's say an AC generator here. So remember, commutator is the split ring, if you do remember, yeah? So what is the job of this split ring in a generator, you can say? So we can say, simply, it will convert alternating current, AC current, into direct or pulsating direct current, you can say. So take a look at this. For example, this is for, let's say, the current that is generated in AC, let's say, okay? So let's make this one a bit nicer here. Let's say this is what happens here. What the commutator does, okay, remember, it kind of like reverses the direction of the current so that it's always in one direction. What do we mean by this? It is going to convert this one into something that is the first half, and of course this is the second half because it doesn't allow the current to reverse its direction. So it is always in the positive direction, you can say. So this is what the commutator does, okay? So converting AC into pulsating DC, you can say, or just converting or converts AC to DC, you can say. And that's all for that. Now the last question here, of course, you can say transformer has 150 turns of wire of the primary coil, this much turns on a secondary coil. If the input potential difference across the primary is this much, what is the output potential difference across the secondary? So you're just going to use the equation of the transformer. That is basically V2 over V1, N2 over N1. So V2 is unknown here, the voltage over, let's say, across the secondary coil. So here's V2 plug in the numbers, make V2 the subject or cross multiply, then of course you do the math, you'll get 6 or 60,000 volts, and that'll be the answer to this one here. As for the remaining question, these are extended response, and of course these are all cancel. But if you're just willing to go through them out of curiosity, of course you're the most welcome here. And of course you can have, or you can benefit from the idea of this one as well. You have these information says, what is the electromotive force induced in the ring and all that. So using the information given, of course, you will use the equation for the induced electromotive force, let's say. And of course, using all that, you can find the answer. But once again, if you don't want to go through these or cancel, so that would, or that shouldn't affect anything at all. And of course, it will not be included for the exam. And I'm very excited to finish this chapter. In the next video or in the next session, inshallah, we will start with chapter 7, okay? And of course, chapter 7 is a bit, you can say it is shorter than this, of course, and it is more interesting. But what I want to, before we jump to the chapter 7, let's say, make sure that you go through chapter 6. It might be a bit long, it might be a bit, let's say, I don't know, like frustrating, but of course, this is the chapter that where you can collect most of your marks, let's say, per, you can say chapter. So you have a very good chance. The concepts are easy. Best luck trying. If there is any concept you haven't understood, make sure you go through the videos and you self-study, like do the math yourself, remember the equations, try to know the answers of the questions, and hopefully that would help you to understand all the questions and all the concepts. And hopefully it will lead to get you to the marks that you desire. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.